Hey everyone, Miss Butler here. I have a video on galvanic cells. All right, looking at this picture here, you can see that there's little cups of water labeled A through F, and there's little stopcocks at the bottom here that we can open up. So I want you to just look at this picture and use some common sense here. What letter cup has the highest potential for gaining water? If I open up all of those stopcocks to let the water flow naturally, what cup do you think has the greatest potential for gaining water? Pause the video and I want you to take a guess, circle it on your page. Hopefully you agree with me here that the greatest potential for gaining water is cup D, followed by A, then C, then B, then F, then E. And then we could also say the opposite. Who has the greatest potential for losing the water? It would just be the reverse order. E, F, then B, then C, then A, then D. So we can look at this picture and see who has the potential to gain the water and who has the potential to lose the water. And we're going to connect this real quick to our current unit on electrochem. So this is a chart. We actually have one that hangs up in our classroom. It's called the standard reduction potentials. And what we need to know is we have these half reactions here, and we have some voltage values, these E cell values we'll talk about a little bit later. But the idea is that the half reactions towards the top of this chart with these very positive values have the greatest potential for gaining electrons, whereas the half reactions that are down low on the chart, they have the greatest potential for losing electrons. So similar to what we just looked at with the water, these half reactions have a high potential for gaining electrons. These have a high potential for losing electrons. Here's another kind of version of this chart. Obviously, they left out some reactions, but we know that gaining electrons means that the element is reduced. And so if we have our top reaction here, this is the most likely to be a reduction, high potential for gaining electrons. But we know that if the F2, that fluorine here, if this element is reduced, that makes this the oxidizing agent. Down low here, these have the greatest potential for losing electrons. So lithium here has the greatest potential for being oxidized, which means that this guy is lithium. Because lithium is being oxidized, it is a strong reducing agent. So that chart we just looked at is the standard reduction potential chart. And so those are half reactions that are written on the chart that measure the tendency of a chemical species to acquire electrons. And we know when we gain electrons, that means we are reduced. So every species has its own reduction potential that's inherent to it. But the main thing here is that the more positive the reduction potential, the greater the likelihood that that chemical will be reduced. So the more positive the reduction potential, that chemical really wants electrons. Gaining electrons means it's likely to be reduced. So those little E standards on the chart are the reduction potentials that we're going to look at. How do those numbers come to be? Well, they are measured against a standard, which is the reduction of hydrogen. So here's the half reaction for the reduction of hydrogen. And what we did is we set this reduction to 0. So at standard conditions, 25 Celsius, 1 molar if it's aqueous or some sort of concentration solution, and then 1 atmosphere of pressure, okay? This guy is going to be 0. And on that chart, I had highlighted this reaction and it is set at 0. So anything that's more likely to be reduced than this reaction would have a positive value. Anything that's less likely to be reduced than this particular half reaction would have a negative reduction potential. So all of those E values, those E standard values, represent or reflect reduction potentials. If we needed to look at oxidations, we would just reverse the reactions and change the sign if that's what the question is asking. But typically, we are thinking about in terms of reduction. So we've talked about what electrochemistry is. It's the study of these reactions that are changing chemical energy and electrical energy, right? The types of reactions where electrons are transferred from one thing to the other. And those are redox reactions. Why would we do and study these reactions? Why do we care about electrochemical reactions? Well, when we transfer electrons, we can generate an electric current, And that will help us have, if it's thermodynamically favorable, that electrocurrent can be used to do other things. So if I use that electric current, I can produce chemical changes in other reactions that maybe wouldn't necessarily be thermodynamically favorable on their own. So it's all cool and dandy if we have these reactions where electrons are transferred from one thing to the other, these redox reactions. But how do I actually harness this electric energy? How do we make it useful for us as humans? We can use something called a galvanic cell, which is a device in which chemical energy is changed into electrical energy. So we're essentially taking these electrons and finding a way to physically transfer them from one thing to the other and use that transfer of the electrical current. How do we do that? Well, we need a few things, and one of those is an electrode. An electrode is an electrical conductor, and we use it to make contact with something that's non-metallic in a circuit, right? We know that electrons can run through wire. That's how we get electricity at our house. We have all these wires everywhere, right? But we need some sort of metal piece that can stick in these aqueous reactions, right? The non-metallic part, the aqueous portion of the galvanic cell. There are two types of electrodes that we're going to use. One is the anode, and usually when we draw the pictures, we draw the anode on the left, just kind of as practice. Does that always happen? No. Would I put it past the AP exam to mess you up and put it on the right? No, I'm not sure. It's just all about perspective, but typically we draw it on the left. And the anode is where oxidation occurs. So I remember anox is where the oxidation occurs. Okay, and the cathode is the other electrode, and it's usually drawn on the right, but this is where the side of the galvanic cell where reduction happens. So I'm thinking animals here. I got an ox and red cat. Reduction, cathode, anode, oxidation. Okay, here is a typical galvanic cell, and I know this is a lot to take in, so let's break it down. We usually have two beakers or containers that hold some sort of salt solution, so an ionic something dissolved in water. So here's the two beakers. Okay, in this particular one, I'm going to have some sort of salt that has A2+, this made up chemical A with a positive 2 charge. There's a negative anion as well that would be attached to this. Okay, and on this side, I have B2+. Cool. Okay, these are separated containers, but we need a way for A and B to react. So we're going to connect those with electrodes. So this is a piece of solid A. So it's not the ionic form. It's a solid neutral metal that sticks in this aqueous solution. And this is solid neutral B that sticks in. So this is a way for us to connect the two cells of the galvanic cell. Okay, here's what really happens. When we get this started, we will have some of the solid A lose 2 electrons and turn into more A2+. Remember, there's already some A2+ in here, but it's going to break off because when A loses 2 electrons, it forms A2+, and that's aqueous. It will dissolve. And so what do those 2 electrons do? Well, these electrodes are connected to a wire. And this is a voltmeter to measure the voltage. You could put a light bulb or something like that here to show that there's electricity, but this would just measure the voltage. And so the 2 electrons that left are going to travel along the wire, and they're going to go into the other cell, and they're going to go through this metal B. And what happens in this solution? Well, we have B2+ that's floating around in here, and it's going to be attracted to those negative electrons. And so what happens to B2+ when it gains 2 electrons? It becomes solid B. So we're actually going to get more B sticking, solid B sticking to the side of this metal. So this left side here is called the anode because oxidation was happening here. A went from A to A2+ because it lost electrons. Leo, oxidation, lose electrons. That happens at the anode, anox. And when those electrons came over to the cathode side, the half cell called the cathode, right, then we had our B2+ gaining electrons to form more solid B on the electrode. So this is our reduction. So that's essentially how a galvanic cell works, and we can harness this electricity to do things for us, like power a light bulb. There's one other important component, and that's this salt bridge. The galvanic cell, after a while, after really a short amount of time, we're going to get a backup of charge. If negative electrons keep moving to the right from the anode to the cathode, we're going to get a buildup of negative charges over here because all of the B2 pluses are going to be joining on, and their negative anion that was left floating in here, right? If this was like with a chloride or a nitrate, right? Whatever that other part of the salt is, we're going to have a negative buildup here. And that's not going to last very long because we don't like to have a buildup of charge. Same with over here. If we keep dumping off A2 pluses, we're going to have a buildup of positive charge. So what we do is we put a salt bridge, which is basically a material that allows, like, honestly, the cheap version is a paper towel. We can soak stuff in. Another version is like a sponge. So we soak it in a neutral salt, one that won't impact the reaction, potassium nitrate, potassium chloride, things like that. And what will happen is this aqueous salt, the positive ions like the potassium will actually start to move to the right to balance out the charge. And the negative ions like the nitrates or the chlorines will move this way to balance out the charge. That way this thing can keep running and we don't just get a buildup of charge. Picture like a big stop. Those electrons won't be able to move anymore. One year on the AP exam, they actually asked students what the purpose of the wire was. And so just to be clear, I know it feels like common sense, but the electrons are what's traveling along the wire from the anode to the cathode. So from the oxidation to the reduction, anode to cathode. And so that is how we get the electricity. The movement of the electrons from the anode to the cathode on the wire is how we get the electricity. Let's just recap that salt bridge again. So this salt bridge is what's necessary for the current to continue flowing. And it basically allows us to close the circuit. And so the ions will help make sure the charge of each electrode stays near zero. One side is losing electrons. We don't want to build up a positive charge there. So negative ions move that way. Same with the other side, just opposite. And usually we're going to pick something that won't interfere. So again, the positive ion travels on the salt bridge towards the cathode. The negative anion travels on the salt bridge towards the anode. All right, there's lots of memory tricks in this one, right? An, ox, red, cat. Leo says gur, oil rig, right? We've seen a lot. Here's some more for you, right? I need tips to help us remember. So we remember big, fat, red cat. So the fat, the T, those are positives because the cathode is thought to be a positive charge. Also, the positive ions on the salt bridge usually travel towards the cathode. Red cat, reduction at the cathode, and big fat, right? The fat cat part is because in the cathode, that metal electrode over time actually gains mass because we saw that B2 plus is going to gain electrons and form solid B, and that gets kind of stuck to the sides of the electrode. So what happens then is over time, we will see that that electrode actually gets fatter and gains mass. This one might be a little insensitive. I'm not trying to be, I'm just trying to help you remember, but really what I was taught and what I remember is the anorexic anode, because as the cathode gets fatter, the anode actually has part of the solid dissolving into the aqueous form as it loses electrons. So as it dissolves into the aqueous solution, it's going to lose mass, and so I remember anorexic anode. All right. So what we can do is we can actually calculate what the voltage will be on the wire. That's called the cell EMF, this E standard for a reaction. So first thing we need to do is we need to decide what is oxidized and what is reduced, and we look at that chart of reduction potentials. The more positive the reduction potential, that is the half reaction that's reduced. The other half reaction is oxidized. We're going to write both equations as is with their voltages, and we're going to use this equation to calculate the EMF for the cell. We're going to take the reduction of the cathode minus the reduction number of the anode. So we just take those numbers, cathode minus anode. When we go to balance these redox reactions, right, they're all written as reductions. So once we've calculated the E cell, we can now do our half reaction balancing method. But in order to do that, we need to reverse the half reaction that we said would be oxidized. So we'll flip the reactants and products, and we'll balance the two half reactions just like we've been doing in class when we learned how to balance redox reactions. One thing that's important, we do not multiply the voltage values. So my tip would be to calculate the E cell before you balance the equation so you don't confuse yourself. If you multiply for example, the oxidation by 3 so that you can cancel out electrons, you don't need to actually multiply the oxidation value by 3 when you calculate E cell. It's just exactly how it's written on the chart before you balance. And then finally, you will add up those half reactions. So in my opinion, I'm a much better teacher when I can actually show you examples. So let's do this one together. We want to balance the reaction and calculate the standard cell potential for this reaction. So I have two half reactions here and the E cell values from the standard reduction potential chart. So the first thing I notice is that the first one is more positive, and because these are reduction potentials, it means that that first half reaction is the reduction and the bottom one is the oxidation. Red cat, so we know the reduction is going to happen at the cathode and the oxidation is going to happen at the anode. The equation we saw on the last slide was that the E cell is going to be equal to the standard reduction potential at the cathode minus the standard reduction potential at the anode. So I'm going to take 0.80 volts minus 0.77 volts, and my standard cell, so V is for volts, like a voltage, is going to be 0.03 volts. So that is my my standard cell potential for the reaction when these two are in the galvanic cell. Let's now balance this redox reaction with the information that we know. So to balance, we need to flip the oxidation reaction, because right now my oxidation is actually written like a reduction. It's gaining electrons. So when we write our half reactions, I'll do the reduction first. Ag plus an electron makes Ag. For my oxidation, I'm just going to reverse. Fe2 plus makes Fe3 plus an electron. All right. I see that the elements are balanced. There's no oxygens or hydrogens. There's one electron. So we are already ready. We are ready to smoosh these together. Ag plus and an electron, Fe2 plus. There's my reactants. Ag solid, Fe3 plus, and an electron. My electrons will cancel out, and so I am left with Ag plus and Fe2 plus makes solid Ag and Fe3 plus. There's my balanced reaction. In this, the charges are necessary because this one is going from a positive to a neutral, this guy from a +2 to a +3. So those charges are very essential to this balanced redox reaction. All right, here's another one. I would like you to calculate the standard cell potential using that new equation, E reduction at the cathode minus E reduction at the anode. And then I want you to balance the redox reaction. So I want you to set a timer for 2.5, 3 minutes. I'm going to put the answer up in 3, 2, 1. All right, hopefully you notice that the more positive, so the negative 1.66, that's our reduction at the cathode, oxidation at the anode. Be careful, we are minusing a negative here. So parentheses help, a negative minus a negative, and that what we were minusing the negative of was larger, so our E cell is 0.71 volts. I took my reduction as is, I flipped the oxidation, and then I noticed that my elements were balanced, but I have 3 electrons and 2 electrons, so I needed to multiply those by 2 and 3 respectively. When I smooshed them together, my 6 electrons were able to cancel, and my balanced redox reaction is right there. All right, you should be able to look at a picture like this and also do what we just did in the last problem. So let's figure out how we go through this. So first of all, I see that I have a solid aluminum and aluminum 3+, and that aluminum 3+ is dissolved in aluminum nitrate. So this nitrate is just a spectator. I'm going to write this reaction as if it were a reduction. So aluminum 3+ would gain 3 electrons to form solid aluminum. So basically, we would gain the correct number of electrons to make it this solid electrode. On the other side, I have solid lead, and then I have lead 2 nitrate. So really, this also is should have a +2 right there. It got erased on accident. Because we have lead with a +2, nitrate is just my spectator. So let's write that also as a reduction because we're not sure which one is actually the reduction yet. So that would gain 2 electrons and make our solid lead for this electrode. So we basically have a solid and ion, solid and ion. Okay, on my chart, I am going to look up E reduction, and I get negative 1.66 volts. E reduction, and I get negative 0.13 volts. So I'm looking here, and it looks like that my more positive is the negative 0.13, so this is reduction, and that's the cathode. So this must be oxidation at the anode. So on this side here, because lead is going to be reduced, so this is our cathode, we are gaining electrons. This side would be then our anode, we are losing electrons. And that's usually how it is, anode on the left, cathode on the right, but you can never be sure. I can also draw electrons on the wire because I know the electrons always go from the anode to the cathode because they're oxidized at the anode and reduced, gained electrons at the cathode. So sometimes it'll ask you to draw the direction of the electrons on the wire. That's what I did there. You can see it would go through the voltmeter to measure what the voltage is. Let's calculate that voltage. We know that we're going to take the reduction, so the cathode, negative 0.13, minus the reduction value at the anode. So my E cell is going to be 1.53 volts, and that's what this voltmeter would say, 1.53 volts. I can also fill out the salt bridge. The salt bridge here is made of KNO3. That is positive potassium and negative nitrate. And so the K plus ions are going to go this way to balance out that charge. And the NO3 minus ions are going to go towards the anode. So the positive ion towards the cathode, the negative ion towards the anode, so that the circuit is complete. I can balance these as well. My reduction half reaction, we leave the same, Pb2 plus 2 electrons makes Pb. My oxidation reaction, we have to reverse when we start to balance. So it'd be Al makes Al3 plus and 3 electrons. So we're going to multiply this guy by 2, multiply this guy by 3. That way, when we smoosh, our electrons will cancel out at 6, and we get 3 Pb2 plus 2 Al. Oops. Let's try that again. That's an arrow. There we go. Plus 2 aluminum makes 3 Pb solid plus 2 Al3 plus. All right. Here is your job. You need to fill out everything on the galvanic cell. So I'm expecting to see what solutions are in the beaker, what the anodes and the cathodes are made out of, which direction the electrons are moving. I want to see a salt bridge. I want to see a balanced half reaction, and I want you to calculate E cell. That's a lot of work just giving this guy right here. So we know that one half reaction will be in the anode, one half reaction will be in the cathode, and it'll be your job to figure that out. I suggest you start by assigning oxidation numbers to figure out what your oxidation and your reduction are for this reaction, and that will help you find anode and cathode. So pause the video, set a timer. Let's do 4 to 5 minutes for this one, and I'll put the answer up in 3, 2, 1. All right, my first step here was to assign oxidation numbers, and I saw that manganese was reduced and sulfur was oxidized. So here's my oxidation half reaction, and here's my reduction half reaction. So for oxidation, we know oxidation happens at the anode. What I see here is because these are all ions, these are all going to be aqueous in solution. And then it said it's acidic, so I just tossed some H plus in there as well. When we don't have a solid metal as part of our half reaction, we are going to use something that's a neutral metal like platinum, PT, and that's solid. So this platinum will not interfere, but it will allow the electrons to go from my HSO3 minus to my SO4, and as it turns in, I should say, my electrons go from the HSO3 minus along the wire, and then it is oxidized into the SO4 2 minus. So this is a neutral metal. I had to put both my reactant and my product in solution because they were aqueous ions. Same with this other side. There's my 2 aqueous ions, some H plus because it's acidic, and I use platinum as well. So I'm going to balance these half reactions. I needed to add waters and H pluses, 2 electrons here. I needed to add waters, H pluses, and 5 electrons. I multiplied, I canceled out, and simplified my H pluses and my waters to get my overall balanced equation. Just a reminder, on the wire, the electrons go from the anode to the cathode, and then you do need a salt bridge. I did not specify what I would put on the salt bridge, but just that the positive ions would go towards the cathode, the negative towards the anode. Finally, here are these half reactions. I found the voltages from the chart. These are both written as reductions. Here's those values, and I take the cathode minus the anode and get a 1.30 voltage on the wire. All right, one more practice for you. I just have 2 half reactions, cadmium 2 plus and cadmium, tin 2 plus and tin. I want you to find the half reactions on your chart that have both of these. Well, obviously, one would be reactant, one product, but they're all written as reductions. And I want you to tell me what goes at the cathode, the anode, and calculate the cell potential. I will put the answers up in 3, 2, 1. All right, so hopefully you noticed that tin had a more positive reduction potential, reduction at the cathode. So here is my reduction reaction that's happening. The ions would gain 2 electrons and form a solid. And then at the anode, we have oxidation happening. So I had to flip what the chart said because this is oxidation, but solid cadmium would dissolve into the aqueous cadmium ion and then give up those 2 electrons. I did my cathode reduction minus my anode, and I got a cell potential of 0.267. All right, one way to describe a galvanic cell is called line notation. The AP exam doesn't use this a lot, but your textbook does. So instead of drawing a full picture or describing in these long paragraphs what the galvanic cell looks like, they will write it this way. They're going to do what the electrode is at the anode with a line. They're going to tell you what's in the aqueous solution at the anode. They're going to do a double line to show that it's separating the anode from the cathode. They're going to tell me the aqueous solution at the cathode, a single line, and then the electrode. So this helps us see what the electrodes would be, especially if part of the half reaction does not tell you the electrode. Like platinum, for example, is not written in the equation. Platinum just serves as the electrode, even in the example we just saw. So we have platinum, right? And then we would have whatever the aqueous solution is there. So your book will do this. I just wanted you to be able to comprehend. Anode is on the left, cathode is on the right. The outsides are the solid electrodes, and then the aqueous solution contents are in the middle between, and then separated by that double line. Your book will also ask you to give a complete description of a galvanic cell. So I just wanted you to know what they're asking for. They want the cell potential. So they want you to do your E reduction of the cathode minus E reduction of the anode. They want the balanced reaction, so that's the balanced redox reaction. They want you to tell you the direction of the electron flow, so either showing it in a drawing on the wire or explaining what direction they're moving. They want you to label what the anode and the cathode are. And then if they specify for it, I would ask you to add the line notation. If they don't specifically ask for line notation, then you can skip that part. So hopefully this gives you a good overview. We are going to do lots of practice in class and watch some video footage of how these actually work.